Okay, let's talk about momentum. Momentum. Oh, that should be an M. Let's see if I can get rid of that. U-M. All right, so first of all, let's talk about momentum is a vector quantity. So first, get that down. V-E-C-T-O-R, right? Vector quantity. You know what that means. It's got magnitude and it has direction. So when we want to talk about the momentum of an object, we just say that P, which stands for momentum, is equal to M times V. And this is a vector. The little arrow over it indicates vector again, and that's a vector. So again, just to reiterate, remember I'm multiplying a scalar times a vector. What do I get? I get a vector. And so if we want to talk about the linear momentum of any object, such as a pretty little car, like that pretty car, it needs to be, they'll probably release that next year, maybe with a Jaguar next 2015 model edition. And it has a velocity v, it has a mass m. If we take the product of those two, we end up having the momentum of the object in kilograms times meters per second. Okay? Momentum gets its derivation basically from Newton's second law. Well, not, and if you just were to take F equal ma, so here's a vector, right? Scalar times vector. And then you do a little bit of simple substitution. What you can get to what causes the object to have a change in its momentum, which is an impulse. And I'll talk more about that here in just a minute. So take a look at this. F equal m times, but a is delta v over delta t, right? Change in velocity over change in time. And if you move the delta t over, you end up getting F delta t equal m delta v. And what this F times time, so think about that, the force times the amount of time it acts on a body. So for instance, if down here underneath the car, the rear wheels, like we have a rear wheel drive car, and so that means the drive wheels are in the back, and it's pushing back on the earth, and so it's pushing with a net force for a long period of time, then you'll have a large change in momentum. So hope that makes sense. Basically, your velocity will change a lot. So if you the common name for force times time is impulse, and then I always like to write it out. Impulse is equal to a change in momentum. See if I can squeeze that in there. Okay, so basically, the larger the impulse, the larger the change in momentum on a given object. So what can impulses look like? Well, for instance, you could, let's just take, for instance, that's the floor, and you got a ball, and the ball is falling down towards Earth, and it hits the Earth, and then it bounces back up. It's the bouncy ball. And so I'm going to displace the ball over just a little bit to make my picture easier. So then the ball gets bounced back up. So the ball is in contact with the Earth, the floor, for a period of time, and there's a force acting on it, and that force is always in this case, it would be in the upward direction, wouldn't it? And so that force times time causes a change in momentum, and that leads right with, if you think about it, F equals ma, Newton's second law, that whatever direction that force is, the net force, to be clear and more concise, in other words, the sum of all forces, whichever direction that force is going, the direction of it, it will be the same for the A here. Same. You could say the same is true for the impulse momentum equation. That the direction of the net force will be the same as the direction of the change in momentum of the object. So you've got impulse equals change in momentum, and so think about this right here. So if we were to plug in with this concept right here. And sort of put it to use, so we have F delta t equal m delta v, and if you say, okay, well, what's the delta v in this case? Well, let's choose downward to be negative, so we'd have force times the change in time. That's the time that it's in contact with the floor, and then times the mass times the velocity final minus the velocity initial, and so. If you look at it from that way, then think about this. If you put in the downward is negative, I'm sorry, the upward is positive. Is that right? Yeah, upward would be positive. Let me erase that. There. Okay, so velocity final is positive, correct? Because it's going up, so this would be velocity final. Final, there we go. And this would be velocity initial. So what happens when you put a negative velocity in? So a negative of a negative is a positive. So guess what you would do? You would actually add the velocities together, thus giving you a large change of momentum, which makes sense because bouncing is usually is a large change in momentum. It's a pretty big, drastic, violent change. And whereas if you think about it, if it was just like for instance a lump of clay and it hit and stuck to the floor, then you'd only have a velocity final, and that would be the only velocity change that you'd have because it would immediately go to zero. So velocity final would be zero, and then velocity initial would be some number, and you would not have that bounce, so it would not be as drastic. So if you think about that, that's actually what they try to do in cars. So when a car crashes, they try to get all the energy to go into the car around you, causing basically a non-bouncing situation, and they also try to increase that impact time and make it much larger so that it takes as long as possible to bring you to a stop. So for instance, seat belts, airbags, crumple zones in cars, all of that is in there and put in place to try to make it so that the time increases, thus the change in momentum of your body in an impact is not as violent. So that's pretty simple, I guess. So that's the concept of impulse. And you can a common thing that is very easy to look at is that they like to do a force times time graph, and be force here in newtons, right? And let's just take a look at a couple different lines. So what about that line right there? So think about that. What would that area, and you can write that in there on your notes, but I'll write it right up here. What would this area represent? And then so if you knew that, you knew the mass, would it be possible to find the velocity or the change in velocity of the car? Think about what that area would represent. And an easier one would be just what if you actually, let's use just a pretty blue, what if you had a line like that? So could you find that area? I know they're superimposed on each other, but you can see through it. And that area would see, either one you could be given to try to find information about an object. But see if you can answer what that area would mean. Okay? I'm going to leave you with a simple setup here. So, well, real quick, we're going to find the area. So, and then you're going to set that equal to, think back to the equation I just told you, impulse equals change in momentum. And then I'm going to leave you with a simple thought on the conservation of momentum. Conservation of momentum. So this is your first inroads into a conservative system. And so basically what we're saying here is that momentum is all about transfer. So when you have an impact with something, you transfer some of your momentum to another object. And in our world, we're going to have pretty ideal situations. So we're going to have momentum. Well, it's always conserved, but momentum, we don't have to worry about things such as friction and that. Momentum is always AWA ways conserved. So what that means is that it's sort of nice because if you can figure out how much momentum you have going into a system, then you know that within that closed system, that momentum will remain a constant. So a simple case would be a car that looks like that, and it has a velocity that's going in this direction, and to the right, we'll say. So it has a velocity v, and that's a vector quantity, remember. And it's going to strike and hit this car, which is at rest. So here it comes, and they're going to hit each other, and they have this little device like train cars where they sort of coupled together. They stick together. So this is the before, and so if we could know everything about this system before, then basically what it says is that we will know, I wonder if I can finally lasso, and then copy, and then paste. Hey, I'm getting good. Okay, so we will know everything about it after. So, but what's different about it after? Well, afterwards, these two have coupled together, and so now the mass of the system that's moving has increased. So think about that. What would happen if the mass increased? What would have to happen to the velocity if mass times velocity gives you the linear momentum of a system, or the, of that object? So what would have to happen to the velocity if the mass increased? And that's what the law of conservation is all about. It's just about two objects, maybe two or more objects, striking each other, hitting each other, combining together or bouncing off of each other, and you have to answer questions about, how do I go about figuring this out? So there's all kinds of different situations that you can look at. So you could have a ball striking another ball. So here comes the ball, and it's going to strike this one, but now they don't stick together. But still, momentum is conserved. So if this one had momentum and this one did not, then it could give all or some of its momentum or to this ball over here. We'll call this A, and then B, and then think about this. What if it hits it at a glancing blow? What if I sort of rotate it just a little bit? Like maybe it goes this way, so it's gonna glance off of it right there. Well, then after the system is over, now think about this. Momentum's a vector quantity, so that's the direction that the momentum's going before. That means if it's conserved, it has to be going that way afterwards. And I'm going to wrap up here with this. But think about this. If it hits B, this is sort of like pool, isn't it? This would go off this way. I'm just generating angles here, random, and then this would go off in this direction. And so, but if you think about this, the sum of their two momenta, their x components, or I'm sorry, I got to go backwards. Here, let me get that. There. Okay. This one's component along that axis, and we'd have to have the information to figure this out, and this one's component, so B's component, and then these two components, how would I do that? So maybe it has a component going off somewhere like this, because that looks at about 90 degrees. I'll just do it like that at 90. And then like this, these two components would cancel out, this one and this one. Can you see why? Because think about it, there was no momentum in that axis. I'll highlight that part. I didn't highlight it. In that axis right there. If there's no momentum there before, this is assuming my everything's good in my drawing, then there can be no momentum there afterwards. And so that's a good way to stop tonight and let you sort of let that sink in, and maybe use your book just to read a couple little sections about impulse and look at the graphs in there and see if you can come up with a little bit better understanding of it. All right?